elements, this is another kind of homework problem, under isomorphisms. I actually intended to say this before we did the example, but so fact that you guys are going to prove actually, if f g to h is an isomorphism, then I mean you want to say how much. So in some sense, an isomorphism between two groups will preserve as much structure as you can think of. Right? I mean, it's an isomorphism meaning it really looks like the other group. So the first fact is that f of the identity, we already talked about this, is always sends to the identity in H. So here's G, here's H. Here's the identity. We know each group has an identity. If it's an isomorphism, it actually has to map the identity to the identity. Right? That's not a property of a general bijection. Right? Bijections can move things around however they want. If it's an isomorphism, then it actually has this property. If X is in G, then where does it send the inverse? Well, this is another homework problem I'm not going to prove for you. It actually sends it to the inverse of the image. So, f of x goes somewhere in H, and it's going to be, the inverse of x will get sent to the inverse of f of x. So in some sense, preserve inverses in this way. Another thing is if G is cyclic, with generator, say, x, then H is cyclic with generator, can you guys guess it? F of x, right. Now remember, those are not going to be unique generators. You can have many generators for a cyclic group, but this will be one for you. So you kind of saw this in the example of the Z5 star and the Z4. Well, we went from the Z5 star, we took the generator, which was 2 in Z5 star, and we set it over to 1, which is the generator in Z4. So that was an example of that. Okay, so the first two, I think, plus another one is on your homework, and you might see something like this on your worksheet on Thursday. So I just want to keep these on a list so you have kind of in your notes. Actually, let me put the last one that's on your homework, is if x and G has order n, then f of x has order n. So just some bullet points here to have in your, just in one place. I think that's useful. Okay. So like I said, a bit more about cyclic groups in the 7 minutes we have. So more about cyclic groups. So this is chapter 11. So our main theorem, let me just recall this, we've already used it before. Our main theorem says that there's not many cyclic groups. There's sort of one for every cardinality. Right? There's only one cyclic group up to isomorphism. So let me just write this down. Our main theorem says that if G is cyclic of order n, then G is isomorphic to what? Zn plus. Right? Your favorite cyclic group is actually the only one. I mean, there's only one cyclic group up to isomorphism. If G is cyclic of infinite order, then G is isomorphic to, what is it? Z with plus. Okay, so cyclic groups are nice. They're simple. There's not many of them. There's exactly one up to isomorphism for every cardinality. Okay. Now the second theorem about cyclic groups is about their subgroups. So what about subgroups of cyclic groups? Well, here's another theorem. I'll call it theorem 2, or this is what he calls in the book, but of course that's just arbitrary. That the subgroups of cyclic groups are not interesting in some sense. They are also cyclic. So every subgroup of a cyclic group is cyclic. Okay, so that's a priori non-trivial statement, right? I mean, you have a cyclic group, and it could be that the substructures in there are actually something else. They have some other structure, but it turns out that every subgroup of a cyclic group is actually cyclic. So on your exam problem, recall in Z10, right? I asked you guys to write down the cyclic subgroups of Z10, but you were actually writing down all of the subgroups. So the subgroups of Z10 were, well, again, I phrase it as all the cyclic subgroups, but they are actually just all of the subgroups. There's no other subgroup. You get the whole thing. Of course, you always have the zero and the whole thing, and then the sort of two the proper subgroups will be these guys. These are actually all of them. There's no other subgroups. So these actually consist of, these are all of the subgroups. Okay. And let me give you the 4-minute proof. I can prove this in 4 minutes. I hope. Yeah. Does the statement make sense? Is that clear? So any subgroup you have actually has a generator to it. 0, 1, 2, 5 in that case. Or others, right? The generator is not unique. So here's the proof of theorem 2. So, the picture to have in mind, I think the book draws this picture. Here's G. So let's suppose G is cyclic, right? We're gonna assume that G is a cyclic group. Let's say it has a generator, I don't know, A. So G is a cyclic group. It's got A squared, it's got A cubed, etc. It's got E somewhere. That's A to the 0. And then let's let H be a subgroup. And let's suppose it's not just a trivial subgroup, because if it's just the identity, then yeah, it's clearly cyclic subgroup is generated by 0. Okay, so let's assume that it's actually a non-zero subgroup. It's actually more than just a 0 element. So in our picture here, what we've got is, we know H has the identity, right? The H is a subgroup, so it contains the identity. But every element in G is a power of A. So this guy also consists of A to some powers. Maybe I'll be suggestive here. Everything in G is A to a power, right? That's the definition. So H itself is sort of a sub-collection of A to some powers, right? It's some family of A to a power. So let's let N be the smallest integer, positive integer, such that A to the N is in H. There's got to be some N, there's got to be some integer such that A to that power is in there, because it's not just the 0 group, right? There's some power of A in there, by assumption. So I'm going to claim that that is actually the generator for H. So let's do this quick. So claim H is actually equal to just A to the M, A to the N, all the powers of it, right? So what is this? This is A to the N to the M for all M integers. So somehow I was writing A cubed, A6, A9, that's the sort of suggestive notation I'm making here. Well, let's prove the claim. Let's let A to the K be some other element of H. Yeah, be any element. Okay, so I pick some other A to the K. And I want to write a to the k as a power of a to the m. Are you guys with me? Right. So if it's really if h is actually just all the powers of a to the n, this guy better be a power of a to the n. Okay, well let's use the division algorithm. Remember I mentioned that this comes up a lot in this context. This implies that I can write k as equal to qn plus r for, the usual story. I'm dividing n by k, and so this is going to be for r between, 0 strictly less than n. So, a to the k, you guys seen this before? This is a to the qn plus r, which is the same as a to the n to the q times a to the r. But check this out. So now you've got, this guy is an element of h, right, by assumption. This guy is an element of h because a to the n was in h. And a to the n to a power, of course, is still in h. So this guy is in h. That means I can multiply by the inverse of this element, which is an h, multiplied by this guy, and I'll get a to the r. So what that implies, can you guys see this? A to the r is actually in h because you've got two elements that are in h that are multiplied by a to the r, and so you can multiply by the inverse of this to get rid of it, and you get a to the r. You've written a to the r as something in h times something in h. Subgroups have the closure property. So what's the contradiction now? Well, what's the conclusion? Is that what does r have to be? It has to be 0, right? Because if it was anything else, it would be a positive integer that's less than n. And we've chosen n to be the smallest positive integer such that a to the n is an h. This implies that r equals 0. And so, in fact, k is equal to qn. Okay, k equals qn, and that's what we wanted. So the last thing is a to the k is actually a to the n to the q. That's what we wanted. So every element of h is indeed a power of this generator. And a little rush there, I'll let you digest that. I might have something like this on your worksheet, but that might be a useful fact to have for your homework. I wanted you to see it. Okay, so I'm in my office hours now, right, 11. And then otherwise, see you guys Thursday.